Bon appetit. And today the title of my talk is Near Surface Investigation with DAS and Geophysical Method. I will briefly introduce some studies I have conducted in my PhD time. So if I have enough time, I'll review all this content, but if we do not have enough time, so I'll focus on the first two parts of the study, which is the surface wave dispersion inversion and the full waveform inversion. So my research is about the near surface investigation. So what is a near surface? A near surface is just an area like 100 meters under our feet, right? So the left figure is a photo that I took last November in Calgary. This is what the near surface in Calgary is like. And the right figure you are very familiar with is the near surface in Boston. The near surface area is kind of challenging to deal with, mainly due to several reasons. So the first is because the near surface area, it consists of unconsolidated sediments with low velocities. So the wave energy will get trapped in the near surface, and it also lead to some challenge to our grid meshing at the near surface because we need to satisfy the stability condition. The second is attenuation at the near surface is very serious. So it can distort the waveform and makes our data processing more difficult. The third is the ground roll will dominate the near surface. So usually in exploration geophysics, we treat ground roll as noise rather than signals. And the ground roll has very large energy. So it will overwhelm other signals like reflection wave or diving wave. The fourth reason is the topography. So it can have some irregular topography, which will lead to inaccurate measurement of our seismic data. So in our study, we want to use the surface wave to investigate the near surface. Our first question is how we can utilize these surface waves. So we need to know what are some features of the surface waves. We know in 2D cases, if we ignore the anisotropy, the surface waves are mainly Rayleigh waves. They propagate along the surface, and they have two important features. One is the Rayleigh waves are dispersive, which means it has the different frequency wave will travel at different speed, and also it is multimodal. So it has several motion patterns that travel with different times. So as shown in the middle figure, you can find it is dispersive, quite dispersive, and you cannot see my pointer. Okay. So it consists of the fundamental mode and the higher order mode, as shown in the middle figure and the right figure. Another reason I want to conduct surface wave for near surface investigation is also because we have some DAS experiment in our field research station in Cruz before. And if we collect the data from the trench deployed DAS fiber, you could find because the DAS fiber data, they are mostly sensitive to the axial horizontal direction. So that's why the collected data are mainly beautiful Rayleigh waves. You can not see very obvious reflection wave, but you can see very beautiful large energy surface waves. So this is a principle of the DAS. So the DAS is mainly, it is measuring the time delay and the frequency shift of the bank scattered light in the fiber to measure the strain of the fiber. So it means when the seismic wave hit the fiber, it will generate a strain in the fiber. And by continuously measuring this phase shift of the bank scattered light, it can measure the strain of the fiber. This is mainly principle. So compared to the traditional displacement measurement or velocity measurement, the dust measure the strain or the strain rate. So this is the background information of my study. And first I will review the first part of my study, which is based on the dispersion curve inversion. So in this part, I will briefly review three parts. The first is theory, and the second, I will introduce some synthetic tests, and the third, I will show some result applied to the dust field data. As for dispersion curve inversion, we first need to know how the dispersion curves are generated synthetically. So given a layered velocity model, as shown in the left figure, it's a layered velocity model, and we know the layer thickness, and we know the Vs, Vp, and rho in each layer. We would generate a multimodal dispersion curve that's shown in the right figure, like this. Here we're using the propagator matrix method. And we can also find the dispersion curves are mainly sensitive with respect to shear wave velocity rather than primary wave velocity or density. So that's why in our inversion, mainly the shear wave velocity is inverted, but not the P wave velocity or the density. As for the inversion, here we use the Bayesian-based transdimensional inversion method. The transdimensional means during the inversion, the model size, which is the layer number in our case, is unknown, and it will be explored during the whole inversion. During the inversion, when we incorporate another parameter, which is the model size, layer number k, the new posterior expression is changed to the bottom one. So here, the transdimensional inversion is implemented using the reversible jump MCMC through a burst depth scheme. The burst depth scheme is just like this. During the inversion, we will have a probability to insert a new layer or remove a layer or perturb a layer. So the burst depth scheme is like this. And in the test, we compared the transdimensional MCMC result with a fixed dimensional MCMC result. So here you can find the first figure is a transdimensional inversion result, and the left three figures are the fixed dimensional MCMC result. We can find compared to the other three, the transdimensional inversion result can yield the most likely velocity model without bias due to over-parameterization or under-parameterization.
But transdimensional just means that you can change the number of layers.
Yeah, you can change the layer numbers. Yeah. So the layer number is treated as unknown, and it will be explored during the inversion.
Thanks. That's one of them to understand.
Yeah.
The words.
I like this a lot.
Thank you. And also during the inversion, we incorporated multimode dispersion curves. So the new likelihood function is a product of the multimode likelihood function. And this is the new likelihood formulation for the multimode inversion. So the advantage of this inversion method is first, the layer number k is unknown and it will be explored. And also, not only the model parameter is updated, the error is measured and estimated during the inversion as well. And we also incorporated the higher order mode to improve the resolution. To make the computation more efficient, we incorporated parallel tempering. So we generate several Markov chains simultaneously, and it will allow a more dynamic state exchange between different Markov chains. So this can help our inversion to converge to a global minimum faster. Here are some synthetic tests. We first generate the synthetic dispersion curves as shown in the black line. The left figure is the fundamental mode, and the right figure are the multi-mode dispersion curves. And we add some noise, combining the random noise and the correlated noise in our synthetic data to generate the observed data, which are shown in the red dots.
So this is phase velocity?
Yeah, this is
super
phase
low
velocity.
res, hard time.
Oh,
And,
it's very
I-
unclear.
I missed the beginning of your talk. I was a little distracted, as you saw. How do you compute your phase velocity from the waveforms?
Waveforms, if you have the waveforms, you need to conduct the tau p transform and FFT. Tau p transform.
Tau P,
Tau p
No,
transform.
tau p transform. It's a time
yes.
frequency.
transit time, and P is slowness,
Yeah, pure slowness.
Oh, okay, so it's a time frequency type transform.
close to, yeah.
And another is FFT.
There's delay
Is it
time,
with jerks?
delay time slowness, which is related to the frequency wave number.
Okay, yeah, so we can transform the observing data, like the waveform data, into another domain, which is the velocity and the frequency domain.
Do you take the propagation matrix and you set the determinant to 0?
For synthetically generated the dispersion curve, we use the propagator matrix.
Yeah.
But for the observing data, we use the transform to transform it into the other domain and pick the dispersion curves.
And are these curves from that?
These are generated synthetically using propagator matrix.
Yeah.
Using
That's why the synthetic curves always look good. Much
yeah,
better
yeah,
than the data ones.
right.
That's
Yes.
good. Thanks. That's what we were talking about. The Schulman
Yeah.
determinants, the same thing.
Mm-hmm. Yeah.
Too many words for the same thing.
So we conducted transdimensional immersion both on the fundamental mode dispersion curve and the multimode dispersion curve. The left figure here, it shows actually there's a black and white dashed line. It's not very clear on the screen. So the black and the white dashed line are actually our true layered model, like VS model with depths. But here, if we use only the fundamental mode, in the left figure, you can find these intermediate layers, the second layer here, it cannot be resolved. But if we use like multi-mode dispersion curves, you can find all the layers can be resolved. So this means if we incorporate more modes of dispersion curves, it can add more constraints on our model, like both at the shallow part and the deep structure of the model, and also the uncertainty at all depths are reduced. We use the collected samples to generate the predicted data, and we plot the predicted data as shown in like the colorful strips. So we can find this predicted data can match with our observed data very well, both for the fundamental mode and the multi-mode. But the results are quite different. So it is not related with our inversion method. It is actually related with the data limitation of the data and the model relationship. It's because the data is quite limited to characterize our model. And later we applied this method to some field dust data. This is a field dust data deployment. We actually collected the data from the straight dust fiber with 1 kilometer, about 1 kilometer in length, and the fiber is buried at 1 depth meter trench, as shown here. So here we compared the collected dust data with the co-located geophone data. The first row is the dust data, and the second row are the geophone data. In the first row, we can find the dust data because it's dense sampled, so it's quite continuous, and it does not have the instrument response as the geophone, so the low frequency component can be well kept. So we can find also from the velocity and the frequency spectrum in figure C, we can also find it has clear multi-mode dispersion curves, and the low frequency components are well kept.
So the dispersion curve would be like the dark red part on the right.
Yes, yes, the high energy.
Yeah. Pretty good reconstruction, actually.
That's amazing.
Yeah.
That's really clear.
Yeah, yeah,
and
yeah.
advanced data, and
Mhm.
geophysical is much worse.
Yeah. The first reason is also the geophone data has some spatial aliasing artifacts. Because the spatial sampling is very large, it's 10 meters, but for dust fiber, the spatial sampling can be 0.25 meter.
Right.
So that vary a lot. And also geophone data has instrument response. So you can find the data below 12 hertz. You cannot recognize
Right.
those information.
Where is 12 hertz here? Because I don't.
Oh, it's okay. Sorry, it's here. Like
Oh
you
my,
can
yeah.
find, yeah,
Like at a fifth of your or a quarter of your
yeah. So sorry for the indexing. And another important thing for the real data processing is actually the dispersion curve peaking. If we want to like have accurate inversion, we need to peak the dispersion curves very cautiously and accurately. So here, to make our dispersion curve peaking more accurate, actually combine the method of FK filtering with dispersion compensation. So dispersion compensation is not a mysterious thing. It's just you shift the a certain mode of dispersion curve to be around the zero time area, and then you filter the other modes with other velocity, and then you shift it back like that. So the interference from the neighbor modes will be removed if we follow this way, and we can find the in our filtered data, the dispersion curves are more clear for peaking. And this is inversion result. We conducted transdimensional inversion on the fundamental mode and the higher order mode. The left figure as a result of the fundamental mode inversion result. And the middle figure here is the result of the multimode dispersion curve. We can find there are some fine layers are resolved in the multimode result, and also the uncertainty are reduced a lot. So here are some conclusions for this part of study is first, we use the transdimensional inversion to implement multimode surface wave dispersion inversion, and the data errors are estimated and involved in the posterior. But this method still have some limitations is because in this inversion method for the forward model, for the forward modeling, we use the propagator matrix method, which is based on the layered model assumption. So it is hard to characterize lateral variation of the velocity model. So that's why we later conducted another study which is for waveform inversion.
Can we ask questions before you move on?
Sure.
So is there an intuitive link between the number of dispersion curves you have and the number of layers? Does the number of dispersion curves tell you something about the complexity of the model?
Yeah, it is. They are related, but it's not very obvious. Because for example, if your model change a lot, but sometimes the dispersion curves are also very close. So it is not very obvious, but at least from here.
When you say layers, you mean different media. If it's homogeneous and you have a number of layers, hopefully that doesn't affect the curve much. Is that true?
Yeah. So here from this figure, you can find this is a fundamental mode dispersion curve. Actually, here for each frequency, it has a velocity.
Yeah, so those are all different on each layer. That's going to affect.
The velocity is different on each layer.
Yeah.
Sure. Yeah, absolutely.
So
but is it fair to say that the number of dispersion curves you have is proportional to the number of different layers that you have? Or is it unrelated?
it's not related like that. For example, if you have different velocity models, you always can generate like 5 modes of dispersion curves. You can always generate 5 mode numbers of dispersion curves.
Okay.
The difference is if you have different velocity models, like the velocity values for each frequency, it will be different. So the mode numbers are always fixed.
It's always 5?
Not 5. It can be many modes, like
Infinite number.
Yeah.
So the contrast between layers could have like a surface wave because of the contrast, but if there's no contrast, then that surface wave could go away.
yeah,
So if the
yeah,
contrast is weak,
yeah.
that mode goes away. But if the contrast is strong,
Sure.
that mode is more important.
Theoretically, it
So
can be
both
But that
numbers.
doesn't, I'm sorry, that doesn't really answer my question.
okay.
If you have a homogeneous Earth, how many dispersion curves do you have?
Homogeneous, it does not have the dispersion
It
curve.
doesn't have any dispersion whatsoever.
No.
If you have one layer and then another homogeneous or a bit
That's
underneath.
one. For the homogeneous, only the radial wave.
Yeah, that's right.
Yeah,
So that's
the
one.
radial function, you have
Right.
3 roots, but only
Right.
one root
Oh, but
smaller than the.
It does not have any dispersion because there's no velocity change, right?
You can change the frequency and you will have the fundamental.
But
velocity.
it's homogeneous, so the velocity is constant.
It's cursive, I think.
No,
You can change the. Oh, no, 0.92, yeah, for homogeneous, the radial wave is 0.92 times the absolute velocity.
So it's
It-
constant. It
is-
will does
it's
not have
constant,
dispersion
it's
curve.
Okay.
You need at least 2 half spaces.
Yeah, so it
Yeah.
at least has 2 layers of
One
velocity.
strip, one half space. How many dispersion curves do you have then?
One.
You have
Because-
one for really? And now you have an extra one?
For my case, or
No,
in borehole,
no,
we have
no.
infinite.
Infinite.
For borehole, we have infinite number of the.
But in a
What
model,
about in this case, I'm saying, so one strip, one homogeneous strip, and one homogeneous half space underneath it.
It will have one dispersion curve because the multimode it is generated from the interference between of the wave reflecting between different interfaces.
Mhm.
So it can only have has only one interface, so it only have one dispersion curve. It is kind of related like that, but in real case the media are very complex.
Mhm.
So theoretically it can generate like unlimited modes.
But as you can tell, I'm trying to go from simple to complicated.
Yeah.
And so if you have a homogeneous half space,
Mhm.
you have one dispersion curve for Rayleigh waves, or you have no dispersion curve then. in that case.
It's just like
constant, yeah.
it's just
So if
straight
you
line.
have, but in this case now, you're
Mhm.
gonna have 2 curves, the constant one and another that dips, or?
Yeah. And no, there's no constant. Then it just has a fundamental mode.
Or
Like
just one? Okay.
yeah, just
Now, if
one.
you have 2 strips and then a homogeneous space, you're gonna have 2 curves?
Perhaps 2 or 3. I'm not sure. I'm not sure
But
about
this
this.
is
like doing fence over it.
Yeah, so I'm so sorry, I don't really know about sense. But there's no like traditional theory that tells you that what the number of dispersion curves is. You don't have that. There's no like standard theoretical argument for the number of dispersion curves. Because I thought it would be like number of roots or.
It's like the polynomial. I'm working on the.
Yeah, we'll talk later. We'll let her finish
Flat
her
layer. But
presentation.
for the flat layer, yeah, after you multiply all the probability matrices together
Yeah.
and calculate the determinant, you will find that is a polynomial.
Okay.
But only part of the roots are can be regarded as a
Physical.
because
Yeah.
some of the roots are imaginary or the velocity is faster than the absolute velocity. So that part of the roots need to be get rid of.
Got it.
So it depends on the number of variables and the number of boundary conditions, really.
I don't think that related to there is an explicit relation.
It must, because it's the degree of the matrix. The more boundaries you have, the bigger the matrix gets.
Yes. Not bigger of the matrix, but when you multiply the matrix, you will have the higher order of the polynomials in the determinant.
Yeah.
Yeah, and when you solve that polynomials, you will find the
More roots.
small roots. But for in the wormhole case, because you have the Pascal function has an infinite of roots. So even you have only one layer, you have the
Okay, well, let's talk about it.
Okay.
In your last experiment, do you know like the local channel surface geology? And
Yeah.
That,
Yeah, we have some well-logged information.
how well does it match the inversion result?
Actually show it here, but this figure is not very clear, so I didn't introduce it. This figure here actually, as the right part, actually add the background, the geological information here. So here I did a comparison with my result. It shows it matched with the geological information. But it's not very clear, so sorry, I can share my slides to you later, if you want to.
So I'm looking on my phone, velocity as a function of depth. That's what the right side is, the color.
The right side, it has three geological formation. One is glacial till and the sandy shell, and the sandstone formation. It has, so our result can generally match with the interfaces of this
Yeah.
geological background. And the geological background information is from our well-logged data.
Yeah, that's good.
Okay, so for FWI, actually know that FWI has a lot of like challenging problems. For example, the FWI is quite nonlinear. It is a very nonlinear problem, and it also suffers from solution non-uniqueness. And it will fall into cyclescaping. A lot of methods are developed to deal with the cyclescaping. And also, if we do a multi-parameter inversion, we will also suffer from the crosstalk. And it rely on the initial model a lot. So yeah, there are a lot of challenging problems in FWI. With respect to these problems, we have different solutions. For example, actually, the FWI is inversion, so it's always like the mapping from the data to our model. We could use different misfit functions to extract different information in our data to characterize our model. For example, we could use the most conventional waveform different misfit function, or the envelope-based misfit function, or the amplitude different misfit function. They are sensitive with respect to different part of our model, and we could also add some regularization to our loss function to better characterize our model based on some prior information. And for the optimization method, and we have the conjugate gradient, LBFGS, and the truncated Newton method like that. In practical FWI processing, we could incorporate many strategies, like we could do some low frequency extension thing to recover the low frequency component, and we could do a multi-scale strategy, and we could combine different misfit functions to reduce the non-linearity of the problem. So here we developed a multi-step, multi-scale surface with FWI. On the left, it is a workflow of a simple FWI workflow. We just conduct a pre-processing of the data, and then we put the data into the waveform difference misfit function-based FWI, and then we got our inversion result. But actually, the real data processing is more complex. It needs more strategies to be incorporated into the workflow. So first, after the pre-processing, we conducted the travel time inversion, travel time cross correlation inversion. So here, after the travel time inversion, we got a initial model, and this part of inversion can reduce the non-linearity of the problem. And later, we conducted FWI with fundamental mode and the higher frequency component of the data, so that we could have a good characterization of the shallow area of our model. And we conducted the third round of FWI with waveform difference and multimode surface waves. So we can characterize the model from the shallow to deep structure to get more details of our subsurface model. So here we conducted test on the synthetic data. So figure A here is the true model, and the figure B is our initial model, and the figure C is inversion result using the low frequency component with fundamental mode surface waves. And the figure D is the inversion result of using the high frequency component combined with fundamental mode surface waves. So comparing figure C and figure D, we can find because the high frequency component and the fundamental mode, they are mainly sensitive with respect to the shallow part of the model. So it add a good constraint on the shallow part of the model, but low frequency component and the fundamental mode, they do not perform the same way as the figure D. So here, that's why we kind of conducted a reversed multi-scale strategy in the inversion, which is use a high frequency component with fundamental mode first. And here, we show the result of the travel time inversion in figure C. After the travel time inversion, the result is not very nice, but it gives us a generally good initial model for the following inversion. And in figure D, we show the result of using the one-step FWI and with the multi-step FWI. So we can find with or without this multi-step strategy, the result is using this multi-step strategy, the result is improved. You mentioned about the geology information here. We show some geology information. This is our well log data and some geological information like we got from CMC. So the geometry is the same as the last study. Just in FWI, we need to conduct more processing steps. First, we need to convert the string rate data to velocity based on the plane wave approximation. And we need to build our initial model. And the initial model, you need to build it cautiously. For example, for VP and rho, we could build it based on the well log data up to with Gaussian smoothing. And with Gardner's rule, we generate the density initial model. For VS initial model, we just used the inversion result of the previous dispersion curve inversion and build the initial model based on that. We also
the attenuation, something.
QS is attenuation initial model. And also we need to do some filtering both on our seismic data and the wavelet. The wavelet is clouded wavelet. It's shown like this. So for the first round of FWI, we conducted anisotropic FWI without the attenuation consideration. So figure A is the initial VS model, and figure B is inverted VS model. We also conducted a small test to show the importance of the low frequency component. So here, if we do not have remove the low frequency component below 12 Hertz, we can find there are some aliasing in our imaging in figure C. Sorry. And these are some seismogram comparison. So after the inversion, we can stick to the fourth column of the left panel figure. So we can find the residual has reduced a lot after inversion. As the near surface is quite suffer from the attenuation a lot. So that's why we also inverted for the attenuation parameter, which is QS. Here, the figure A is inverted QS model. Based on the inverted QS value, we updated our VS model again. So the figure B is the updated VS model. And the figure C shows the VS model difference compared with anisotropic FWI without consideration of the attenuation. Here we show the difference in seismogram, and we can find the waveforms can match better with our observing data. So this is the summary of this part. We conducted a 2D shear wave velocity. We investigate the near surface with FWI, and we use this multi-step, multi-scale strategy, and it improved the near surface imaging resolution. And we used a sequential inversion with Q estimation to help improve the accuracy of the velocity inversion. And a third part is we actually also conducted FWI on the VSP dust data. So here, this is a misfit function as before. I just showed the like how the VSP data and the VTI media is incorporated in the FWI. This is just some formula derivation part. Yeah, we'll just say some synthetic test. So here we generate some synthetic model like this. So figure A is the model perturbation of VP. Figure B is a model perturbation of the density, and figure C is VPH, and figure D is VPN. So VPH is a horizontal velocity, and VPN is a NMO P-wave velocity. So these four anomalies actually are distributed at 4 different locations. If we conduct an isotropic inversion, so the result is shown in the left figures. We can find the VP can be recovered generally while, but for the density is a disaster compared with our true model. So usually we call density as a garbage collector in our FWI, right? It's always hard to very well invert for the density. But if we consider the anisotropy, we can find both the VP density and the VPN and VPH can be well resolved. So this small synthetic test just showed us if we ignore the anisotropy in FWI, our inversion result might be not very accurate. And later we applied this VTI FWI on the well dust data. In the well dust data, this is the dust deployment in the wells. So we have 2 monitoring wells. The dust street fibers are deployed there. And these are the raw data shots collected from 2 wells and their amplitude spectrum. And we built the initial model similar as before, and generate the initial model. This is a result of isotropic inversion without considering anisotropy. And this is a result generated using isotropic, anisotropic FWI. And through comparing these figures, we can find the resolution actually got improved a lot. So these are some comparison for seismograms and the waveforms. And the misfit function dropped with VTI FWI and isotropic FWI, and some comparison with our well-log data. So the summary for this part is we found the anisotropic parameters are not very easy to invert, but it have a influence on our inversion result. And with the dust data, because that dust data has low frequency component and dense sampling, and we could have a better better resolution of the subsurface model. And that's the main point of this part of study. And this is the content I want to share with you for today. I'd like to thank my PhD supervisor, Kris Innanen, and my co-authors, Yang Danmer and Wen Yong, and Daniel and Donald for their help. And also thank NSERC and the scholarship that supported during my PhD study. And thank Yue Su for the invitation for the seminar. And thanks Joshua for the technical support. Thank you.
Well
Thank
done.
you.
I have to step out. I apologize. I have to go teach.
Oh, okay, no problem.